Hey everyone, my name is Cheyenne Bagshmali, and here is my physics project, the physics of active noise cancellation. So, have you ever noticed that noise canceling headphones are really effective at blocking out low, constant sounds like airplane noise, but they don't work as well for voices or sudden sounds? Now, why is that? The answer, well, comes down to wave physics, specifically interference and how sound waves behave at different frequencies. And in this presentation, I'll explain how active noise cancellation, or ANC for short, and why it's more effective for low frequency sounds. So let's continue. Now, what is a sound wave? Well, sound essentially is a type of mechanical wave that travels through air as compressions and rarefactions. We can describe sound waves using a few key properties, these being frequency, amplitude, as well as the phase. Well, frequency tells us how fast the wave oscillates, and the wavelength is the distance between the repeating points. And amplitude tells us how loud the sound is. These quantities are related by the equation V equals F lambda, where V is the speed of sound, and frequency is measured in hertz, and wavelength is in meters. So regarding wave interference, that's one of the most important principles in wave physics, is the principle of superposition. This means that when two waves meet, their displacements add together, and if the waves are in phase, they combine to produce a larger wave. This is known as constructive interference. But if they're exactly out of phase by approximately 180 degrees, they cancel each other out. This is known as destructive interference. Mathematically, if we add two identical waves that differ by a phase of phi, the result is zero. This idea is the foundation of noise canceling technology. Now, how does active noise cancellation work? Well, it uses the principle of destructive interference to reduce unwanted sound. First, a microphone on the headphones detects incoming environmental noise. Then, the system generates a sound wave with the same amplitude but opposite phase. This new wave is played through the speakers and overlaps with the original noise. Because the waves are out of phase, they interfere destructively and cancel each other out, reducing the sound that reaches your ears. This process happens continuously and in real time. So, noise cancellation does not work equally well for all sounds, and we can see that low frequencies are actually easier to cancel. From the equation of V equals F lambda, we can see that when frequency increases, wavelength decreases. And it's much more effective for low frequency sounds than high frequency ones. Low frequency sounds have long wavelengths that change more slowly over time. This makes it easier for the system to generate an inverse wave that matches the original sound in both amplitude and in phase. On the other hand, high frequency sounds have short wavelengths and change very rapidly. Because the wave is changing so quickly, it becomes much harder for the system to match the phase accurately. Even small mismatches mean the waves do not fully cancel, which is why noise cancellation is less effective for high-frequency sounds such as voices. Now, in conclusion, active noise cancellation is a practical application of destructive interference in wave physics. By generating a sound wave that is equal in amplitude and opposite in phase to incoming noise, the system is able to reduce unwanted sound. However, this process is not equally effective for all frequencies. Low-frequency sounds are easier to cancel because they have longer wavelengths and change more slowly, making it easier to match the phase. High-frequency sounds, on the other hand, have shorter wavelengths and change much rapidly, which makes accurate cancellation much more difficult. Overall, this demonstrates how fundamental concepts such as wave interference and the relationship between frequency and wavelength in the equation directly apply to modern technology. Furthermore, this is why noise-canceling headphones work best on sounds such as airplane engines, but not as well on conversations. Thank you very much for listening to my presentation. Here are my sources and references, as well as my additional visual references and additional sources. I really hope you enjoyed this presentation, and I hope you have a great day.